X-ray diffraction is a form of materials characterization that, when used correctly, will tell you the components of an unknown material. This video contains a brief overview of X-ray diffraction. This includes background and theory, how to conduct an experiment, how to use the data collected in your experiment, and some applications of X-ray diffraction.
Here is some background information on things you should know before beginning the lab. There are a few simple objectives to keep in mind during this lab experiment. The first is to measure the average spacing between layers or rows of atoms in a crystal. The second is to determine the orientation of a single crystal or grain, and the third is to find the crystal structure of an unknown material. X-ray diffraction has been around since W.L. Bragg and his father first derived what is now known as Bragg's law, an equation that relates the wavelength of the X-ray to the interplanar spacing of the crystal and angle of incidence. X-rays are used in this type of characterization because their wavelengths are on the order of the size of an atom, 1 angstrom. When the X-rays interact with the atoms in the lattice, they can be reflected out either constructively or destructively. Constructive interference means that the two X-rays, as shown in the top photo on the left-hand side, are in the same phase with one another. Destructive interference means that the two X-rays are out of phase with one another, as shown in the top photo on the right-hand side. Whether the X-rays interact constructively or destructively will depend on the orientation of the crystal. This orientation will also change the interplanar spacing value, as shown in the bottom photograph. For these reasons, a powder diffraction will be used in this lab, ensuring that all orientations of the crystal will be exposed to the X-rays. From this powder diffraction data, we will be able to determine the crystal structure and interplanar spacing of the sample. There are three main equations you will use in this experiment. The first is Bragg's law, which is n times lambda is equal to 2 dHkl times sine of theta. Equation 2 relates the interplanar spacing of a cubic system to the Miller indices. dHkl is equal to a over h squared plus k squared plus l squared, all raised to the 1/2. Equation 3 is sine squared theta is equal to lambda squared over 4a squared times h squared plus k squared plus l squared. N is any integer greater than or equal to 1. Lambda is the wavelength of the X-ray. dHkl is the distance between atomic layers in the crystal. Theta is the angle of incidence, and h, k, and l are the Miller indices.
In order to conduct an XRD lab for yourself, follow these steps.
To conduct the experiment, you must first prep your sample using the following: a mortar and pestle, wipes and isopropyl alcohol, a spatula, a powder of some sort, and mounting slides. Once you've compiled all of your materials, you must grind your powder to make it a finer grain. When your powder is at a texture to your liking, you must place it on the mounting slide. To know which mounting slide you need to use, make sure you know which one is compatible with the XRD machine that you will be using. In this case, we will be using the Expert Pro. Here is the mounting for the Siemens D5000 XRD. Make sure to put enough powder and to even it out.
While operating an XRD machine, make sure that you are always wearing your film badge dosimeter. This badge will let you know if you have been exposed to an unsafe level of X-rays. The higher resolution machine is a Panalytical Expert Pro X-ray powder diffractometer that can characterize both powder and bulk samples. Here, the high resolution machine is being calibrated and moving to its initial position. The XRD machine we used for this experiment was a Siemens D5000. This is what it looks like on the inside. Loading a sample into the Siemens D5000 can be seen here. Using the program that is available with your XRD machine, follow your instruction manual in order to start the X-ray diffraction and properly obtain your data.
Now that you have conducted your experiment and retrieved the data, you must do the following to analyze it. The first step is to create a table with 7 columns. In the first column, list out all the 2 theta values for every peak. In the second column, report the theta values, the first column divided by 2. Now in column 3, list the sine of 2 theta values. For column 4, multiply column 3 by a constant value so that every row in column 4 equals a nearly integer value. Round the values in column 4 and list them in column 5. These values are equal to h squared plus k squared plus l squared for each peak. In column 6, list out the Miller indices. For column 7, calculate the lattice parameter using equation 3. Make sure that when doing your calculations to have your theta values in radians. Here's an example of what one row would look like once you have followed the previous instructions to create your table. The final 2 steps with this table include averaging all of the values from column 7 to find the lattice constant with the appropriate error. The final step is to compare these values with the known values of tungsten to see how your material compares to tungsten. After the experimental part is over, you still need to analyze all of your data. For this lab, you were given 2 known samples and 4 unknowns. To simplify this lab, we were told what the 4 unknown samples were: Cu, CeO2, TiO2, and CrO3 to go along with the 2 known samples, quartz and NaCl. For every sample, data will be given in 2 columns. The first is 2 theta and the second in CPS, which stands for counts per second. Plot these columns against each other with proper labeling. Next, plot the data and identify the peak positions for the unknown samples, and from these peak positions, identify which samples belong to which data. XRD has many other uses beyond the scope of this lab. They include identification, polymer crystallinity, residual stress, and texture analysis. The most common application of identification is with powder diffraction. Polymer crystallinity is important as it allows you to find the ratio between peaks of a material and therefore determine the crystallinity within the material. Residual stress is the stress that remains in a material after an external force has been removed. An example of this is bending a piece of metal will leave residual stress after you stop applying force to it. Finally, texture analysis is used to determine the preferred orientation of crystallites within a polycrystalline material. Thanks for watching, and we hope you enjoyed our video.